Okay, so we are talking about significant figures now. Significant figures, they were created or thought about because certain mathematical operations might actually fool you into thinking you have something that's more accurate than what you started with. So let's look at some examples to make this idea clearer. Let's pretend this is my ruler here. Then these marks are 1 centimeter, and so each one of these smaller marks, because there's 10 of them, is a millimeter. Okay? Now, we're measuring this object here, from here to about there. Now, it's not quite exactly halfway. It's awfully close. So we would measure this to be 5 millimeters, or 0.5 centimeters. Now, the issue is that we said that's not quite exactly 5 millimeters, but because my ruler doesn't have any markings that are smaller, we can't necessarily estimate with any kind of assurance how many what fraction of a millimeter it actually is. Because my tool is only so accurate, I can only give one significant figure here. I don't want to write something like 0.48 because this 8 is totally made up. And so, that is why we have to use significant figures. Another example of where significant figures are important, if you have 1 foot and then you divide it by 3, well, you might come out to have 0.3333 feet. Now let's just pretend we're not thinking about inches at all. So this is 3 repeating feet. Now what this is saying is I have one significant figure here, and I'm dividing by 3, and suddenly I have an accuracy out to tenths, hundredths, thousandths, 10,000, hundred thousandths. Now, this is because in a mathematical world, if I took one exact foot and divided it by 3, I would be able to say that I have exactly out to as many digits as I want accuracy. But in the real world, we actually don't know this. In the real world, we just have one digit. And so we would want to round it to represent exactly the accuracy we started with. And so when we divide, we keep it at one digit. Okay, so the moral of the story is you want to keep your significant digits to be the same accuracy as what you started with. You don't want to add more significant digits as you go along. Now, just to be clear what a significant digit is, for example, 5.203. Every one of those numbers contributes to an accuracy. This is 4 significant digits, even though there is this 0 in there. Because there are 1, 2, 3, 4 numbers. So basically what we disregard is something like this. If I write 25,000, we actually have 2 significant figures, because these zeros are not contributing to the accuracy. Similarly, 0.00135 on the other side, this is only 3 sig figs, because the zeros before it are just placeholders. They're not actually telling you a measurement. Now, the trickiest thing here, and this probably will make the 0 thing a little more understandable, 10 has one significant figure. If I write 10 point, what that is saying is that I know it is exactly 10, not just around 10, it is exactly 10. So this would be 2 sig figs. If I do 10.0, I'm saying that yes, I measured it to an accuracy of a tenth here, because I'm adding the 0 to be more precise. This is 3 sig figs. And so it's like saying the difference between I have 10 inches and you had a stick that was like about this long, but you can't measure any further because you don't have any more markings. Or, if you had more markings along the ruler, you could say, yes, even with more markings and more preciseness, I know it is exactly 10. So that is what that decimal is saying here. That is what that 0 is saying there. So, again, calculations should not get more precise as we go along. So, an example of where you would use this in the math. Okay, a ball has circumference of 12.3 centimeters. What is the radius? Now, when we end the problem, we know that we started with 3 sig figs. So when we end the problem, we need to round to 3 sig figs. In the nature of this problem, we're going to get as many digits as we want, but we don't want to fool ourselves into thinking we have a more accurate answer than we really do. Okay, so circumference and radius are related to circumference equals 2 pi r. And so we're going to take the circumference, measuring around like the equator of the ball, and we're going to set it equal to 2 pi r. Now to get this r alone and figure out the radius, we divide by 2 pi on both sides, and I plug that in my calculator. Now when I plug it in my calculator, I got r equals 1.9576058 centimeters. Now because pi never ends, I could get as many decimals as I want. But the issue is that I actually don't have that kind of accuracy. I can only claim to know 3 significant figures here. So in my answer, I only include the first 3 digits. And so because this is a 7 here, I would say that the radius I know is about 1.96 centimeters. And that is as far as I can as I could go. And so another example of this, and maybe this will explain a little more too why we use sig figs. Let's imagine that we have this table. Now someone eyeballs the side using just like a foot-long stick, and he says, it's about 2 feet. That is 1 sig fig. Another guy uses a laser measurement, and he measures exactly that this is 3.7012 feet on the length. Now here's the issue. If we're finding the area of this table, the first guy didn't do a very good job of accuracy. The second guy did a great job of accuracy. Now if they had both done the laser measurement, they would be able to go up to, this is 5 sig figs. But because this is 5 sig figs, and this guy only did a good job of doing 1 sig fig, we can only, in our final answer, stick to 1 sig fig. So, to find the area, we do length times width. And when you multiply that out, you get 7.402. And we would have been able to say that's our final answer if that first guy had measured better, but we have to round to 1 sig fig. So we would say that it's roughly 7 feet squared. So that is why we have to stick to those significant figures. Okay, we're going to do one more example. And this is an example I took from the book. It involves red blood cells. And so they're taking these red blood cells, and they're taking the radius of them. The radius of the first one they measure to be 5.0 times 10 to the negative 6 meters. Now the radius of the second blood cell they get to be 5.1 times 10 to the negative 6 centimeters. Okay, so the radius of the second ball is a little bigger. And they want to find the difference of the volumes. Now, we're going to give you the formulas for most everything you need. The volume of a sphere like this, a ball, is V equals 4/3 pi r cubed. So basically, we are going to take the volumes of those two, and then we're going to find the difference. But we have to take into account our significant figures. So with radius 1 here, I'm going to start working out the volume here. The volume is going to be 4/3 pi, and then you stick in this 5.0 times 10 to the negative 6 cubed. Okay, now this is going back to algebra. The way to figure this out, you apply the power to both things inside here. And so 5 to the third is 125. Times 10 to the negative 18. Because when I apply it here, a power on a power is multiplied. Alright, now here's the nice thing about sig figs. I only have to multiply all this stuff out and then keep that there. So I'm going to my calculator right now. 4/3 pi times 125 is 523.5987756 times 10 to the negative 18. Okay, now we're going to have to do an adjustment here. Remember how I said that this should be right there. It should be after the first leading number. So we need to rewrite this 5.2. And I'm also stopping there because we only had 2 sig figs to begin with. And so I'm going to round after 2 sig figs. Now, this is saying that we would go back 18 with our decimal, but we have to go back 2 more with our decimal here. And so we would say this is because it's going over 2 more already, we would say this is to the negative 16. The other way to think about it is that this number has gotten bigger, and so to make up for that, we have to make it move over negatively less. Okay, now we're going to do the same thing, the volume for this guy, but I'm going to pause recording for a second and just do it on a calculator. Okay, I got 5.6 times 10 to the negative 16. And now the problem is asking us to find the difference. So I'm going to take this, which is bigger, and subtract this, which is bigger, and subtract that right there. So it'd be 5.6 times 10 to the negative 16 minus 5.2 times 10 to the negative 16. Now, by the way, the only reason I could just subtract right away is because these are both 10 to the negative 16, which means they're the same order of magnitude. And so if I subtract, I get 0.4 times 10 to the negative 16. Now this means I have to move the decimal back here. So it's 4.0 times 10 to the negative 17. Sorry, this should have stayed the same as 16. Alright, now here's the only upside to significant figures. If you generally, in the very end, keep to the same sig figs that you started off with, you don't have to worry. I'm going to try to have us get used to sig figs, but I'm not going to be a sig fig Nazi. So do the best you can to just make sure that your sig figs in the end of the problem are going to be the same as the number of sig figs that you started with in the beginning.